Hi everyone, good morning. Happy, we were at Starbucks, they said it was a Tuesday like a Monday, so thank you for coming this relatively early morning, relatively early in the week. Thanks for taking the time. I know it's kind of started summer here, and I was really hoping to have a good turnout for Marcus's talk, and I'm glad there is. So thank you, Amanda, Sarah, Mehmet, and Elizabeth for joining via Zoom. Thank you, Emily, Francis, Brooke, and Nick for joining here in person. I am really excited for the chance to come together and learn from Dr. Marcus Kubsch's talk today. Marcus is a research scientist at IPN, the Leibniz Institute for Science and Mathematics Education in Kiel, Germany. My understanding is that this is arguably, roughly, the leading location in Germany for especially science ed research, but STEM education research too. Marcus has his doctorate in physics education from Kiel University, a background in English teaching and physics teaching, as well as a master's degree in physics education. He's published a lot of important publications, not just publications, in journals including Journal of Research and Science Teaching, the kind of science ed-wide journal for science ed research, International Journal of Science and Math Ed, and Practical Assessment in Research and Evaluation. His research interests are focused on energy assessment models and modeling in science ed and representations, and also some methodological work. A few things that you might not know about Marcus. This past semester, he spent one day of the week teaching physics in addition to a full-time job at IPN. One thing I admire about Marcus is his ability to work within science ed, but also to constructively critique science ed. So when I get really upset about the current system of publishing that requires you to pay $40 to access an article, Marcus is like my fiercest ally in this. And so we spent last night over Thai curry discussing how to reimagine publishing in science ed and take over NARS with an open source publication. He's also great at chaperoning my son around on bike our neighborhood without complaining at all. Thank you all again for coming today. Thank you, Marcus, for taking the time to join us. And so I think the plan will be for roughly a 20 to 30 minute presentation, followed by kind of plenty of time for question and answer and discussion too. So roughly 20, 30 minutes for that. Those of you online, I want to make sure that you have a great experience. So if you have any questions, please just chat. We'll help you out. We can even text you your phone number if you have any trouble with anything. And yeah, at the end too, we'll make sure you have time for questions and engagement. All right, without further ado, thank you again, Marcus.
Yeah, thank you very much, Josh, for this very nice introduction. Well, I will talk about learning progression analytics and how that can help us to really put AI to use for the classroom of the future. And before I go a little bit more into that, what that actually means, I also have a small slide where I want to introduce myself. I think most of that has already been very well done by Josh, but you can get a picture of where Kiel actually is. So here, this is Kiel in Germany, right at the Baltic Sea. And being at the Baltic Sea, that's pretty great because what you can do is you can get sailing. So that's me with my kids on a small little sailing boat. And as Josh already said, I'm really mostly interested in conceptual learning of students, their kind of what we call competence development over time. And that's then related with ideas of assessment and modeling. And modeling both in the sense of how do we model students' learning and understand that, but also the scientific practice of engaging students in modeling. And now I already started to talk about digital learning environments and learning progression analytics. That was in my title. So if we envision what the classroom of the future will look like, I think what we're already kind of seeing is that digital devices like tablet computers are entering classrooms more and more. And this was certainly also rushed by the pandemic, right? That greatly contributed to that. But there are also other things like digital measurement systems that we, for example, especially use in physics education. Or you might have, let's say, a digital thermometer in a chemistry class. And what that gives us is that students are learning in these classrooms and interacting with these devices. It gives us artifacts of their learning, and we can use these to assess students' learning using AI mostly, because if there's an open-ended task, for example, you have a student answer, that's something, if you want to really get real-time evaluation of that, you're going to need AI. You cannot have a human score that. And if we can do this, this really can help us to deliver, I think, on the big promise of digitalization when it comes to learning, and that is, in my opinion, individualized instruction. That really helps all students get to the best that they can possibly do. So if we have these AI-enhanced assessments, we can use it to get feedbacks to students. We can also do like adaptive scaffolding, stuff like that. You might even think about adaptive routes through instructional materials, different learning materials for different students, depending on their interest, for example, or their motivation. And what you can also do is you can obviously give this information to teachers. And then teachers can adapt their instruction to better match the needs of their classrooms. And if you want to really do this, then there's a big challenge involved here. Because you need to be able to validly and reliably assess students' learning from their artifacts that they are producing while interacting in the classroom. And that should not be a standardized measure. I mean, I think we know how to assess students' learning, but you can't have them fill in like an assessment every hour to just get at their state of learning. And therefore, the challenge really is to design a meaningful learning environment based on what we know, for example, like project-based learning, this storyline-driven learning, and still assess students' learning. What we need to put together then is our understanding of like learning progressions and how to support them, is our understanding of, and that's mostly coming, I think, from the learning sciences, like what makes meaningful pedagogical environments. And we also then, to really make sense of this in automatically and in real time, is what is mostly done in, I think, the field of learning analytics. And we need to combine all aspects from these three areas of work. And then at the intersection is that what we call this area of learning progression analytics, where we want to be able to assess students' learning validly, reliably, based on their interactions in the classroom, based on their interactions with digital materials. And this is really a new research area that we've established by IPN for us. And we have two projects where we're doing that. One project is called Alice. That's actually the other one you're not seeing. The first project is called AFLEC. And in the AFLEC project, what we're doing is we're taking instructional units, digital units that were already designed, and we're trying to reanalyze what's going on there, figure out how to automatically assess students' learning in these units, and then develop a teacher dashboard. And now in the Alice project, that's an even more advanced project where we want to really design the curriculum materials with this idea of continuous online assessment in mind. Because what we already figured out in the AFLEC project is, well, would have been great if we have had another task here that would help us to better assess students' learning about this idea, right? But obviously we didn't design these materials with this idea in mind, so it's not in there. So the challenge in the Alice project is really, how do you design meaningful instruction that meets these goals, that helps you to validly and reliably assess students' learning? And in the AFLEC project, we are trying to figure out how can you use great existing curriculum material and still get a little bit in that direction to figure out something about students' learning. And then the remainder of this talk, I will really focus on the AFLEC project. And the AFLEC project is not something we are doing alone at IPN. We have partners. We have partners from the DIP, which is like the educational technologies part, where they are supporting us. And we have educational psychologists from Ruhr University in Bochum. That's Nicole Rummel's group, and that's Henrik Wexler's group, if that may ring a bell for you. And so I want to focus on the AFLEC project, analyzing and supporting learning for the development of competence, and that doesn't really fit the acronym because it's a translation, and the original acronym is German. So what are we doing there? Well, Josh already said that I focus a lot on learning about energy, and then it may not be a big surprise that in this project, it's about learning energy. We had units that focused on students learning about energy, and we have a general model of competence development and learning about energy. The idea is that it goes from manifestations through knowledge about transformation, dissipation, and conservation. And what that means is, manifestation is like, how do I know that energy is manifest in the world? Like, how do I know that there's kinetic energy? Then transformation is about how different forms of energy, like kinetic energy, can be transformed in other forms of energy, for example, potential energy, or for example, light energy in a solar cell being transformed into electric energy. Then there's this idea of dissipation. That means that in each and every of these transformations, some part of the energy cannot be really used anymore. It's going to surroundings. And then we have conservation, that's the idea that energy is conserved over time. And what we know from the literature is that these are these four big building blocks, and students kind of progress through them. And as you can see, what's indicated by these little bubbles there is that at the same time, the learning that's going on is students picking up one idea after another and making connections between those ideas, developing what we will call an integrated understanding over time. And that's really important, that students are able to connect these kind of ideas. So basically, this is a underlying learning model, and this is like the domain-specific ideas that are important here. And now, when it comes to actually individuals learning on an individual level, there are many challenges to this model that this model cannot really resolve necessarily. For example, different individual trajectories. Some curricula start with mechanics, so they start to teach you about energy in the context of mechanics, kinetic energy, potential energy, these sort of things, elastic energy in springs, for example. Other curricula, they start with thermodynamics, so heat, thermal energy, and how that is transformed. And the question then really is, what's the consequence of this for students' long-term learning? What ideas do they pick up? What is more productive over a long time? And we really don't know a whole lot about it. Another thing is the role of missing normative ideas. So what happens if a student doesn't pick up an idea about, let's say, kinetic energy? If a student doesn't pick up the idea that kinetic energy is related to the speed of an object, what will happen to that student's learning over time? And how is that different, for example, if a student doesn't pick up the idea that kinetic energy is related to mass? Does that make a difference? Is one of these more hurtful for long-term learning or not? And we also don't really know a whole lot about that. And then lastly, there's the role of non-normative ideas. So there's also like this, what we would call like student ideas, misconceptions probably as well, everyday ideas that go into learning. For example, this idea that energy is a substance. Some students think of energy as a kind of substance that can flow around. And is that maybe something like a useful stepping stone idea that can really be productive in long-term learning? Or does it stop your trajectory at some point? And what about all these different kinds of non-normative ideas, like there's this substance idea that I just talked about, but also there are ideas about energy being a kind of fuel. Maybe that's a little bit more problematic because fuel can be used up and energy not. So yeah, it's also something we don't really know a whole lot about. And if you want to help students learning, if you want to support them, you have to figure out what is the issue. Are they having non-normative ideas? Are they missing important normative ideas? Are they maybe on different trajectories? That's what you got to know if you really want to support their learning. So that's what teachers kind of have to know. They have to be able to assess individual students' learning to be able to really support them. And the issue obviously is it's pretty hard to do that for a classroom of like 25 kids every time, in each and every class period, right? How do you do that? Well, the idea is let's use technology for this. Let's assess students' learning based on the instructional activities, based on the artifacts they create anyway. And we are doing that in a learning environment that we designed in a previous project. And the design idea there in this previous project was to say, okay, how can we support students learning over time? And what you can see here is for the different classes, so grade 5 to 6, grade 7 to 8, grade 9 to 10 in the German curriculum, you can always see how energy pops up again in different contexts. For example, electricity, mechanics, thermodynamics, optics, these are all different contexts, but energy pops up all the time. And if you remember, this idea was where we wanted students are connecting ideas. And this is a really good opportunity to show to students that ideas can actually connect between different domains. It's a core part why energy is such a useful concept, because it always applies. So you need to point that out to students that energy is a central idea that helps you connect what's going on in your mechanics class and your optics class, for example. So we designed short units that teachers can always use just and pull into their regular instruction. They can use them at specific strategic points. These units are called CRUs. And as you can see, they are designed so that they establish this connection here, for example, between electric and kinetic energy, or light energy and thermal energy. That's the idea. And here is actually a short example of how this looks like. It's implemented in Moodle. Moodle is a learning management system, and as you can see, we have, for example, students may watch a video, and there's text field that they could answer. Other activities besides videos include like, it's a little laggy here, I think. Here's something where students then can write in a forum and chat with each other through the forum. And here you have a task where students can actually put these different forms of energy to parts in the picture where you might see evidence of that form of energy. So this is the kind of range of tasks that we have in these digital learning environments. And here is another example activity. So the task here is students are supposed to explain how solar cells are best mounted on a roof. And now for this example activity, I brought an example answer here. So an example answer might be so that they generate a lot of energy. This means they transform a lot of energy. And the angle is important for that. And that's quite an interesting answer if you think about it, because this first part here, this could be evidence of like a non-normative idea, energy consumption, because it says generate a lot of energy. Energy cannot be generated, right? Energy cannot be produced or destroyed. This might be evidence of students having this non-normative idea. The second part, this could actually be quite good evidence of students having this normative idea of energy transformation. The solar cells, transform a lot of light energy. Maybe not perfectly voiced this idea, but good in the right direction. And then here, this might be an indicator for light energy, this part that the angle is important for that, because we know that the amount of light energy that we have somewhere kind of depends on the angle where the light is incoming. So this might be evidence that they have this other idea about light energy here. And now the question kind of is, how can you basically automatically assess this from students' answers? And in the AFLAC project, we have like data from these 12 short units, these curriculum replacement units about energy. We focused on two units, the laptop and the solar cell unit, because there we have the most data, and together that's data from about like 400 students. And the aims are specifically to automatically assess where students are with their learning at each and every step, and then to develop a dashboard that gives this information to teachers in a way that's meaningful for them so that they can better tailor their instruction to the needs of their classroom. So the question is then, with this automated assessment part, how do you get from a text answer from students, this constructed response answer here, to map that onto our model of students learning? And our answer to that, our approach, is to basically use an approach that combines AI and evidence-centered design. And we developed, that's what I want to focus on here now. And you might wonder what evidence-centered design is. Well, evidence-centered design is a framework basically for designing assessments based on a very strict, or on this idea of creating a validity argument, and what we call an assessment argument. And there's three parts here. There's the domain model, where we really want to specify what is it that students, what do you want students to know and to be able to do with their knowledge. And based on that, you think about what would be evidence that the student has this knowledge or can do this or that with this knowledge. And this leads to the task model, where you want to talk about what kind of tasks can actually elicit evidence for making a claim about students' knowledge, right? I mean, if you want that students are able to construct an explanation and you only give them a multiple choice task, it's not going to provide evidence that students really can use their knowledge to construct an explanation. That's important. And based on that, then you go back to the evidence model and think about how do I have to analyze this data and develop rubrics and models, like psychometric models, to actually work with this to be able in the end to make a valid and reliable claim about students' knowledge. Then, based on this, the question is, how can we use this that we're not developing in the context of this project, where we're not developing tasks, but rather where we have existing curriculum with tasks? How do we use this here? How can this help us? We developed the workflow for this. And we start with articulating a domain-specific model of learning. That's basically our learning progression there. And then we articulate this evidence model. Based on that, we can build scoring rubrics. And then we just score training data with human coders, and then we built an algorithmic model. That's the AI part. And I want to focus a little bit on the evidence model part, because that's really the tricky thing, I think. So what we did is, for each and every task, we kind of came up with this, what we call kind of assessment argument. And in there, you don't have to read all of this, it's just important with the components. We really specify what knowledge is important for a certain task based on our learning progression, what skills are important. And with skills, I mean basically the practices, right? Constructing explanations, modeling, and so on and so forth. And then what we did is we also looked at what we call learning performances, and that's an integration of the practice with basically the knowledge part. So in the sense of 3D learning, in the sense of the NGSS, what can students really do with their learning? And if we now zoom in a little bit on these components, on knowledge, skills, and learning performance, then you can see how the different knowledge components, for example, knowledge that radiant energy depends on radiant power, they link to different bubbles in our model of students learning and the learning progression. So each of these can somehow be linked to parts of the learning progression. Then we have the learning performances, right? And the learning performances are about being able to apply that knowledge in numerous contexts, so they more relate to the big parts, to the building blocks of developing knowledge about energy. And also we have that for transformation. And for each and every one of these statements, we really develop then an evidence statement that clearly specifies what in the specific task would count as evidence that a student has this knowledge, has the skill, or can perform the learning performance. And based on that, we can then develop scoring rubrics and so on and so forth. But this is really where we spend a lot of time in making this a very coherent framework for designing how we want to score things, how they map onto each other, and what inferences we can then make about students learning from individual tasks in our unit. So now, we in the beginning briefly talked about like the domain-specific model. I just talked about how we articulate the evidence model. I think you can trust me that we know how to create scoring rubrics from that. And then there's still this part, the machine learning part. And I also want to delve a little bit into this. How are we actually doing the machine learning part? So let's maybe start off with what is machine learning. So you could think that if you have like two data points or two data elements like X and Y, and you want to think there's some kind of relationship between them. Usually if you have these two data points from some observations that you made, then the relationship between those, that's what nature is doing, right? So if you think of Ohm's law, for example, you measure current, you measure voltage, and the relationship between this is governed by Ohm's law. This is kind of nature in the middle there, it's making the relationship. And now there's like two ways of getting at that relationship, because you need to figure out that relationship if you want to make predictions about something from X to new Y. And the classical approach is basically statistical modeling. Now you try to figure out what nature is doing, what is the model, the underlying model, and represent that in some kind of statistical model, be it linear regression, structural equation model, whatever. And the way you look for validity there is you look at the model fit, and that's what you care about. And then there's the machine learning approach. In machine learning, you kind of don't care about the model in the middle. You use methods like random forests, neural networks, etc., and just let the machine learn from the data what a relation is that can predict Y based on X. And your test for that is then basically get new X's, get new Y's, and see if the model you just trained does a good job at predicting that. And that's a bit a different way to approach this. And so that's what we are doing in this project. And our workflow then is basically to take all the text answers that we have from students. Those are kind of our features in the machine learning talk. And on the other hand, we have the ideas, the skills, of ideas, I mean the knowledge components, right? Skills and the learning performances, those are kind of our labels, labeled by human readers. And put machine learning in the middle. And in essence, this works like this. We have these 2,835 texts from around 300 students. And as a first step, we put them through an NLP step, natural language processing, to represent them in a way that's really helpful for the computer to use in later steps. Then we split that up into like two different data sets, test data and training data. And you just leave the test data alone for now. Then we take the training data and we actually put that into a neural network, train a model, and then once the model is trained, we go back to our test data and see for validation if the model that we trained can predict the test data well. And it actually can. So I'm going to show you on the next slide. So what you can see here is our F1 statistics. F1 is a measure of goodness of predictive accuracy. It goes from 0 to 100. As you can see, for our best doing model, that's the one in the top row. The values are close to 100. And we're doing well on all these different manifestations of energy, on these knowledge elements, and also on the transformation part. We also have two other models there, two simpler models that don't use neural networks but different techniques, and you can see that they are doing, especially in the kind of very simple heuristic-based model, the last one that's based on keywords basically, that they are doing much worse in predictive accuracy. So what we can say is that even from pretty short constructive responses, we can detect these ideas with really high accuracy. So once we're able to do this, we have this relationship between students' answers and how they are doing relative to the learning progression. So now what do we do with that? Well, first thing is we're looking at learning trajectories. What you can see here is students' cumulative score. That is, for each and every task, they get a score based on our automated model, and we just add them up from task to task to task. And these are the different tasks on the x-axis. And you can see in the bluish color, that's like the ideal trajectory if you always score 100% on each task. And in red, the different trajectories that the students actually took. And the black lines there, what they mean, they are parts, meaningful parts of the unit. So that is like end of introduction, end of the first sub-driving question, end of the second sub-driving question, end of the third sub-driving question. At the very end, we have like end of unit. And first, I think what you can see is there's quite a lot of variability in these trajectories. But, I mean, right, you have some trajectories just stopping here, some going pretty straight all the time, some also stop for a time and then go back up. But what you can also see, I think, this is what was my impression when I first saw this, also looks kind of pretty linear somehow. And actually what I did is then basically predict students' score here based on their score here. And this is kind of the first meaningful point where you could think from a curriculum perspective, this is where students should have picked something up. And what you get is actually now square of a linear model that's above 70%. So already after like, I think 7 or 8 tasks into this unit, you can predict the final score with pretty good accuracy. And as you go to later parts in the unit, if you go here, that R square increases to 90% or more, and here it's close to 100%, the predictive accuracy. And that's just based on a very simple linear model. It's not complex modeling, no transformation on data, nothing. Just very easy thing that you could actually do. And I think what's interesting about this is that this gives us a shot at, very early on in a unit, at least identifying students that may need more help, that may be in trouble, that might be missing something. And we could give that information potentially to teachers. Obviously, it's not like a final analysis. We're still working on figuring out some more things here. And part of that is what I'm going to show you on the next slide. Because what you can do is you can disaggregate this score into the different ideas, learning performances, and practices that I talked about in the evidence-centered design. So here, this is the learning performance, so where students really need to integrate the practices with the knowledge in the lens in a meaningful way regarding manifestations of energy. So they have to, for example, explain how and why energy is manifest in some phenomenon, right? And what you can see here is the same logic again, right? Ideal trajectory and just some examples of students. These students are not getting any credit for anything. So what might be going wrong here? Well, maybe you just don't know about the different forms of energy. So let's check that. We can look at the form of electric energy and light energy that is important in the unit. And what we see is, well, students are picking up ideas about electric energy. They are picking up ideas about electric energy, at least to some extent. So maybe what's missing for them is they don't know the scientific practice. They don't know how to write an explanation. We can also check that. And again, what we see is that here, at this task, there are some students that picked up ideas about practice, picked up ideas about electric energy, about light energy. They should be able to do this. So what can you learn from this? You can learn that apparently students in general know what an explanation in science means. They generally know something about electric and light energy, but apparently they really struggle with putting it together in a meaningful way. So a teacher, based on this, if you present this in a better interpretable and more easier to access way, could say, well, I guess I need to help my students with really, putting the knowledge and the elements of the practice together, integrate it, and give support on that, or add in a lesson that helps you with this. And another example for something similar is, we can also look at the transformation part. And here we see, with this idea of energy transformation, that students are doing better. Maybe not great, but they're doing better. And now we can also check again what's going on with students' ideas about energy transformation. So this is a little bit misleading maybe, or puzzling, because it says transformation in both charts, but this is transformation in the sense of meeting the learning performance, integrating knowledge with the practice, and this is just the knowledge of transformation. But there's an interesting other feature I think that you can see here. After this point here in the unit, there's no improvement anymore. So we know that apparently in the beginning of the unit, students get some ideas about energy transformation, but then there's no improvement anymore. So as a teacher, you could kind of, if you got this information early on, use this to say, well, I need to focus on this more. Or we could look at how can we revise the unit, also another possibility. And if you're now able to really make predictions about how students will do based on their scores early on, this is what we have to figure out in the future. You could, give this as kind of a warning to teachers in a dashboard, and they would know how to better support the students overall. So to summarize and conclude, I think what you've just seen is that we can automatically classify short constructed answers with high precision based on students' activities in a meaningful learning environment, right? It's not like they are doing assessments all the time, it's just from the data they are putting in the day-to-day learning. It's like, basically these units are like a digital version of what you would have as a student workbook. And we can forecast the productivity of students' trajectories relatively early. And based on that, our next steps are first to do more in-depth analyses of the trajectories, especially like how are different parts of these trajectories, of the disaggregated trajectories that I showed on the last slide, are interacting with each other, and how does these interaction or interdependency then relate to their overall progress, and so on and so forth. We also want to look at how does other data that we have, for example, data about students' motivation, how can that help us to better understand the trajectories, maybe do better forecasting, and so on and so forth. Then, what we can do is we can, based on detecting students' knowledge elements on these ideas, automatically for each task create a kind of network that shows what ideas students are connecting. And based on that, we can see how these networks change over time, and we can calculate network measures. And based on past research that we've done on this idea of knowledge integration, we're currently looking into whether these network measures can help you with predictive accuracy of the models of when it comes to learning trajectories, it can help us to figure out what's going on, where students are struggling. And also whether this kind of representation is something that may be helpful for teachers. Because here what this will mean is kind of that students are good at connecting ideas between energy transformation, light energy, and electric energy. But what they really struggle with is putting these ideas together with an explanation. And it's maybe a representation that's really accessible to teachers. We're looking into this in a study that our partners at BIF are currently starting to conduct, where they are engaging in a co-design study with teachers about the design of a dashboard. And then early next year, once the dashboard is developed, we'll have another enactment of the unit where the dashboard will be available to teachers, and then we'll see how it works and what the effect of the dashboard is on students' learning overall. And that, I'm at the end of my presentation. Thank you very much.
Thank you so much, Marcus, for a great presentation. Thought it was like great kind of overview and in-depth information on one project. Before, I want to say like two things, just to frame the question and answer portion. Thing one is that we all have different kind of levels of insight into the work Marcus just shared. So in at least three different ways. One is some of us are more experienced with educational research than others. That's great. Another is that some of us are in different disciplines than others, and that's great too. And then third, we have different methodological backgrounds. And so for all those three reasons, you should please, I think, especially if you're a grad student, feel free to ask any question, even if it's like something on slide 2, like something very early on. Those are great questions. In no way are those any worse. In fact, they're often better. They get us thinking about what are the foundations of this work, where it differs from work that you're familiar with. The second thing I wanted to mention is that I love that we have an online component. I want to make this, like, I hope this is a norm for future talks too, but I want to make sure that you online feel not like you are a second tier guest here. So in that spirit, I'd love to invite our online guests to ask any questions first. And connecting back to the first thing, especially any of our two doc students, Amanda and Sarah, but Mehmet and Elizabeth as well. So just to begin, and no rush on this, but just like to invite our Zoom guests to ask any questions of Marcus first. And I think our microphone is working well, so you can just unmute and ask any questions. And if there are none, then we'll switch over to the in-person guests.
I have a quick question, and I'm not sure if you had answered it or not, if I missed it. When you were talking about like the short text answers, did you say that you were able to gather data from that through the AI? And if so, how does that kind of work? Are there like key search terms for understanding?
Okay, yes, we are able to do this. What I actually showed on the slide is that we use different models of how to do this. Mostly, really, I mean, this is part of a supervised machine learning framework where we just, in the first step, code all the answers by hand with actually 2 coders, establish data reliability, and so on and so forth. And then we do the machine learning part. And we did a very simple baseline model based on like key terms. That's what you can see in the bottom row. And as you can see, doesn't do very well model, right? Accuracy is not that good. And the other model that's performing way better, the multitask GBERT large model, is based on the first step where we take the answers of students, the text answers, and represent them basically using BERT. BERT is a big NLP model that is a transformer model that helps you to represent these answers in a way that's better at representing them really in a way that's meaningful and accessible for following machine learning steps. And this is what we did. So this is a big neural network model, the multitask GBERT large model, and that is the one that has this level of accuracy here.
Great question, Amanda. Just as a follow-up, so that bottom row there,
yep.
It's like I don't think you'd call that AI, but it is using supervised machine learning, but you're just using keywords as like the input. You're not using.
Yeah. We basically use use keywords as the input. We filter basically key terms out, and based on that have another step. Basically, I think after the filtering part comes like logistic regression with like lots and lots of parameters.
Yeah, great question, Amanda. So I guess what I take away from your question and your answer, Marcus, is that like sometimes simpler approaches work fine. We shouldn't use a neural network just because it sounds cool, but sometimes it seems like sometimes that kind of sophisticated approach does lead to better results.
Yeah, and I think it's important to kind of use this as a baseline model to check if all the effort that goes into the big neural network model, all the computation and all that, which I mean, also translates into like money and at some point like CO2 actually is worth it. I mean, if the GBERT model was just a little bit better, it probably wouldn't, right? And it can also show you probably if there's something going wrong, because if the GBERT model was just a really tiny bit better, I would be pretty surprised, and it will tell me maybe there's something going wrong in my workflow of the GBERT model. I would be very surprised by that if it was not any bit better anywhere.
Super quick follow-up for you, Amanda. I won't do this for every question, but just knowing that you are just finishing being a full-time science teacher, transitioning to full-time doc student, what do you think of this as a science teacher? I know this is maybe in a first exposure to this kind of approach, but what do you think? Do you buy it? Is it possibly helpful?
Yeah, I think it's very interesting. I have more questions and I want to read more about it in relation to students that have learning disabilities and our English language learners. Just in my experience on some of the terminology they use to try to explain phenomena when they're kind of early on. But I think overall it is very helpful, and I would like to look more into this.
Yeah, I think the point you just made about like second language learners or generally like having issues with writing for whatever reason is important, and we have actually a grad student on that project looking into like different aspects of bias that could come up for this in the machine learning part. It's actually not that easy to do this kind of study, because to detect that you would need a sizable amount of students that actually have issues with writing, and you have to collect data on that, which is always very sensitive data, and that's data you maybe just don't want to collect for data privacy reasons, right? But we collected a little bit of that data, or some of that data, and so we like asked for if there's any other language but German, as we're doing this Germany, spoken at home, as an indicator of language skills. And also, for example, we collected data on gender to see if there's any gender bias in these things, and also on their parents' migration or the students' migration status, so if there's any bias connected with that. I think that's important to work on. And actually, I think there's a study showing that in some cases, if there are spelling mistakes and these kind of things, depending on the actual NLP step, like the natural language processing step you use and how you set that up, you can mostly get rid of issues related to just simple misspellings and stuff like this. And it also kind of depends, I think, on the level of coding that you do, because we don't code in the human coding. We don't the rubrics don't depend on having the right key terms, but rather having the right concept. So if a student, and even there, if, for example, there was a spelling mistake in the answer, if instead of thermal energy, a student said temperature energy, you would still score that as correct, because it's the right idea, it's the right concept. And this way you can also, I think, help avoid bias due to these language issues in machine learning.
So I was standing up just because I want to, Mehmet, I saw a question in the chat. And so I'll read that one aloud for Marcus and for everyone, if that's okay, and then we'll take a few more questions from Zoom. Thank you all. Great work, Marcus. I might have missed it, but my question is, do you have plans to validate this model with different tasks, especially across different contexts, such as biology, different tasks in physics and chemistry?
That's a great question, because that's part of what we're doing in this other project, the ALICE project. So in the ALICE project, we are actually developing curriculum in physics, biology, chemistry, and mathematics, and trying to run this. This is only physics-based, and part of this model will then go to the physics part in the ALICE project, probably. But yeah, we're looking at this, and then there will be interesting questions about like how generalizable are these detectors, these machine learning models across disciplines, yes, all these kind of questions. Yeah.
Great. Any other questions from any of you on Zoom? Great. Okay. Well, we can transition, and you all are still free to ask questions as they come to you if they do.
Mark, one quick question I had is how to interpret these F scores. I'm not familiar with them. And I had trouble kind of intuitively interpreting them, like, hey, is like 90 good,
it's
is
basically,
95
so
better?
the F score is the average of precision and recall, and which might not be very helpful as a definition. So basically, precision is basically the percentage of how many classifications did you get right. So you can have false positives and you can have false negatives, and so there's this measure of precision, which is kind of getting it. You want to avoid false positives. You get a high precision, you get a high score on precision if you have if you have little false positives. And recall emphasizes avoiding false negatives more. So with recall, you want to basically calculate the percentage of the answers you classified correctly from all those answers that basically it's not looking at did you also misclassify something, but it's of the answers that are classified in a certain way are I think it's hard to explain this without drawing things. I struggle with that. Yeah, but basically I think recall is more about like avoiding false negatives. How did I mix these two terms up? Anyway, so basically precision and recall, one of them is avoiding false negatives, the other false positives, and depending on what you want to do, it might be actually something you want to look into. Avoiding false positives may be more important than avoiding false negatives, depending on the context, but typically these are then just averaged in this so-called F1 score, and that's the F1 score. And basically, F1 score of 100 would mean perfect classification. 90 means basically 90% more or less correct classification.
That's a lot. Thank you.
But it's something we are kind of interested in and seeing, especially if you look at bias, for example, are there differences not only on the F1 scores between different gender groups, for example, because that's what you see a lot, but there might actually be differences when it comes to these submeasures of precision and recall. And that might be important depending on what you want to do. Because so let's say you use a machine learning system to kind of flag students that may need support. What happens if you have like a false positive? In the worst case, you're giving a student more help than he or she needs. Probably not a big deal for the student. But think about it. What if you, let's say, put someone in a harder track that's more challenging? That might be really frustrating for a student if you're incorrectly getting into a more challenging track in a digital learning environment. That might be actually hurt the student. And in that case, it may be more important to make sure that to avoid false positives than false negatives.
Really depends on what your goals are. Yeah.
Yes.
I have a question about is it ECD?
Yeah.
Can we go back to that slide?
Yeah, sure. You mean like the general, like how we used it in our
No, the slide that had
the 3 boxes?
yeah.
Yeah.
Yes.
Yeah.
All right. So what knowledge do students have, and then how do we want them to use it? So that was how you developed the actual task that the students did, correct?
Not quite. This is
Okay.
how you would. So ECD was really developed as a means to developing assessment, right?
Okay.
And ideally, this is how you would, and if you were using ECD to develop assessment, then you're 100% right. However, we in this project are not developing assessment. We kind of already have the task, but we have to figure out about what task can give us evidence about what aspects of students' learning.
Okay.
And this is why we kind of came up with this different workflow where we have this kind of iterative process here of developing these evidence models. And so actually this evidence model here on the right,
This is the one.
this is not something that we just wrote down, but it's something where we first started to articulate that, then looked at the answers again, and this was kind of an iterative process.
So is this with the teachers, was this created, in essence, with the teachers that actually completed this with the students that you assess? Or was this done outside with other entities? And if so, who were those individuals?
Yeah, this was done not with the teachers actually implemented the units, because the data that we had, the enactment was already over
Okay.
when we started to look at these or develop these. And so these were developed by basically our PR team at IPN, including my grad student, me, my supervisor, and then we also, when we had a first pass at those, so we have some teachers that are working with us in the department, like permanently, put them pass by them to check back on their expectations there. And after that kind of validation round with the teachers, we kind of finalized them in this way.
Okay, so the teachers who
actually
Who are
implemented the
actually-
units
yeah.
didn't have, were not part of developing these, but
Okay.
other teachers were.
That's fine.
Yeah.
So then my question is, once they do the task, right, the students are doing the task, and you're giving the data back to the teachers, in essence, that's what you're, through the dashboard that you're creating.
That's what we want to do in the future. Right?
So how does that support the teachers making the overall connections that you feel like students are missing? What support is there any?
So I think
Right.
that's a really great question at the core of what makes pointing to the core of what makes a good dashboard for teachers. And the first part of our dashboard development is just finding a representation of the information that we can get from students' data that is helpful for the teachers, or it's easy to interpret. And then the question is like, what is helpful and how you can further support teachers. And we're thinking about like, so we want to do this in a co-design study. So teachers gonna have a say in this, and we're gonna really address teachers' needs in this. But what I've seen in the past, or what I've seen in the literature, what other people are doing, for example, they, if the computer, let's say, detects that a certain kind of mistake a student's making, then dashboard is not only giving that information to the teacher, but also different strategies of what a teacher could do.
Okay.
And that's one possibility that we might look into.
The reason why I'm asking is, just so you know, it's not because I'm like, oh, you need to do this. It's an issue I'm seeing too, where making that connection, that coherent understanding of different tasks and kind of how it fits in that bigger picture is a problem even in undergrad. So a lot of my work is in undergrad. It's a problem in, workforce. I mean, it's just a problem overall. So that's why I asked who designed this, because typically I've seen that this is a problem regardless.
Yeah.
So then now you're giving teachers more information, telling them that there's a problem that exists everywhere.
Yeah.
And so it's like, how are we, because we don't train them. I don't know, I've
Yeah.
never been in Germany. I don't know anything about how you guys train teachers, but I know as a former teacher, I was never trained in how to change.
Yeah.
Right?
Yeah. No, I
How
totally
to,
get that
like,
point. And this
I
is,
get tons of
Yep.
data that says like, hey, your kids aren't doing well at this. And it's
Yep.
like, okay, so
Well,
what
well,
should I do? Do it again. It's
Yeah.
like, do it again, do the same thing all over again until they get it. And it's like, but how do I?
Yeah.
So that's
no, but I
my
think
question.
actually that is why
like,
we have, we're doing this co-design study now to figure that out, what it is that teachers would consider supportive. And I think, that's also something we actively are looking into, and we're very interested in what do teachers need to learn also in their preparation to really be able to engage with this kind of system. And so in the Alice project, we have another PhD student who is from the beginning of the project working on the teacher side of things and thinking about how does PD for teachers have to look like for this.
Yeah.
What are, for example, some beliefs that teachers have regarding these systems, like regarding machine learning, and right? How might this also impact how they can work with this and so on and so forth, and how can you change these things? So I think that's to make this all work in the future sometimes, maybe, the big,
One day.
right, then it's all gonna hinge on teachers being able to get the right information or to make the right conclusions of the information they are getting, and then being able to act in a right way based on that. And I mean, you can support teachers in this by giving, for example, certain hints, by having like educative curriculum materials, but this is really something we also care about and want to further figure out. It's not my focus really. I'm more on the student learning side, and this is also why, for example, I think, right, we won't show teachers something like this and kind of say, yeah, students got these 3 ideas, but not this. This is nothing you could, and being in a classroom, you couldn't interpret that in time for your class, right? This is why I think we need why we are interested in what is a good representation of the information, what is the level of information the teachers actually need. And I think there have been some interesting studies looking at like dashboard design, and they point to that teachers are usually what they want appears to be they want to get a better sense of where students are exactly. But then the question, I think, really becomes of how to transport that information in a meaningful way.
Yeah.
And also, I mean, so even if you showed me as a teacher these 5 students need help, then the issue is still, okay, I'm just one person, I cannot help them all at the same time. So maybe if you could have, for example, a system that would allow you to just send a hint to all the 5 students that have the same issue, more or less, with one mouse click, and then see how they are doing with that. This is also something we are like thinking about, and what is actually starting to be implemented in like intelligent tutoring systems. So I think we can learn a lot from intelligent tutoring systems there and how they work, but I think one issue that I always have with intelligent tutoring systems is that I don't think they reflect what we value as good science learning, where students really engage with the practices and also engage in collaborative learning and are engaging in arguments about evidence with each other, right? Because you're sitting in front of a computer and you're not interacting with your peers, and you're not working with a real experiment. And I mean, online experiments or computer-assisted experiments can be valuable, but at some point, if you never ran a real experiment, right, I wouldn't feel comfortable saying that you actually have mastered that practice in any meaningful way. Yeah.
Thank you all for the great questions. Thank you, Marcus, for the great answers. Thank you all for taking the time to come. Thank you, Marcus, for also taking the time to come and for a great presentation. I really enjoyed the last hour. Presentation, questions, and answers alike. So without further ado, this concludes our talk. We are, though, continuing the conversation somewhere around the corner. I think we'll go get lunch, if anyone's available, over at one of the 2 or 3 restaurants over here in the Union, and then we can sit together, maybe outside. It's hopefully not too hot out. If it is, we'll come inside. But yeah, we'll have lunch on the department. So please come join. And thank you again, Marcus, and thank you all for joining.